And we're going. Okay, cool. So let's talk about the Bohr model today. How far over do I get to go? About here. Okay. Okay, without giving you all the history, which you probably know most of already at this point, I'm going to talk a little bit about this, which is wrong, right? This is not true. It's a model, and it works well for the hydrogen atom, but basically nothing else. And you have to fix it up, which I can show you how to do a little bit of that. But ultimately, this is not the way that things are done, right? We use Schrodinger equation. But so why are we doing it? We're doing it because it gives you the physical foundations to start off. In other words, everybody has these ideas already, and so even though they're not used, they're useful to get a mentality started. All right, so Bohr came to the hydrogen atom right after Rutherford discovered the nucleus. Now, Rutherford discovering the nucleus was in about 1911. And Bohr does his analysis in 1913. And he comes to the analysis via two pieces of information, and one of them was that, hey, a nucleus exists, right? There's this big, heavy thing that's at the center of the atom, and we don't know what it is, but it seems to be the thing that carries most of the mass of the atom. And at that point, you have to remember that atoms were thought of, and people felt pretty good about them because of Einstein saying that they should probably exist, but they didn't know what they looked like. So Rutherford discovers there's a nucleus in the atom, and at a little bit prior to this, someone had done a mathematical analysis of the light emitted by hydrogen gas, and it's known as the Balmer series. Oops, 1913. So Balmer series plus Rutherford nucleus, and Bohr spits out the hydrogen atom, like a model for the hydrogen atom. And his model was pretty simple. It was very mechanical, as you'd imagine. And, well, not quite symmetric, but good enough for government work. There's a radius here. This is a positive proton in the middle, and around it the electron circles, and it does so in concentric circles. And what I'm going to do is see if I can move this a little bit over here so that glare can go away. All right. So Bohr says, okay, I've got these possible orbits. They look like this, and they look like this, right? They go out like this, right? Planets around the sun. And he says that the angular momentum is conserved. Yeah, that's true. But it's quantized in the sense that it can only take on particular values, right? So if the electron is in this orbit, that's great. If it wants to go anywhere else, it's going to have to change orbit. It's got to hop to this one, or then it's got to hop out to this one. And it doesn't exist in between. So this is the first steps of introducing the idea that changes are not continuous in physics and in the physical world. They're not continuous. We observe continuous physical change, but it's not something that actually is happening. So these discrete jumps, right, these quantum leaps, are situations where the electron is allowed to be in, say, an n=1 orbital, or an n=2, or an n=3, or whatever, but not a 2.2, or a 1.5, or a 3.7, or whatever you like. It doesn't exist there. So naturally, this kind of begs the question, why doesn't it exist there? And the reason is, it doesn't exist there. And that's the answer. So if you think about the energy levels, typically what I do is I think of it as a ladder, like a ladder of energy levels. So you take what's called the ground state here. The ground state energy. So this is the energy of the electron in the n equals 1 orbit. Unfortunately, it's often called E naught. Like the ground state energy is usually referred to as E naught, which is somewhat unfortunate, but that's the way it is. So we call that for the lowest orbit. And what Bohr did is he said, okay, if it's in that orbit, it has a particular amount of energy. If it's in the n equals 2, it's got a slightly larger amount of energy, slightly larger meaning quite a bit larger, like this. So this might be the first excited state, which sadly is called E1, but that's for the n equals 2. That's known as the first excited state. And it goes up from there, but notice the spacing is going to change. So by the time, what did I leave here? 2, 4. So by the time you get to n equals 3, it looks like that. And you go to the n equals 4, maybe it looks like this. And you get n equals 5. So n equals 5 might look like this, etc., etc. So it takes successively less energy to jump higher, right? What Bohr was able to do, I should really do this, what Bohr was able to do was give the Balmer series physical meaning. Do you know what the Balmer series is? Right, it's the light emitted, so you'd say, starting here, if I had an electron from the 3 jumping to the 2, it emits a photon. If it jumps 4 to 2 like this, it emits a, well, let's see, I should draw that with slightly lower wavelength. Like this. Okay, it goes 5 to 2. We should do that in blue. Goes 5 to 2, goes like this. I'm going to do the photon going this way now. I can't really draw 6 to 2 at this point, but that would be good if I could. I'll put in the 6, here's the 6 right here, and then you can imagine that there's going to be a drop and a photon coming out. So Bohr assumed a couple of things. He said, okay, look, the electron exists only in these energy levels, which is representative of the orbits, okay? And then he says, anytime an electron makes a transition from one state to another, we'll just assume the dropping, right? Once an electron goes from the 3 state to the 2 state, and again, he didn't talk about how or why that happened. He just says, okay, it's going to drop here. It emits this light. It emits a single photon, right? Anytime an electron jumps between levels, it emits a single photon. And therefore, if you want to excite it, say, from this state back up to this state, you just grab the photon that came out, turn around, throw it back in, and it'll absorb it and go back up. So a single photon emits, as you know, a single photon is emitted by a jump down, by an electron jump down. Okay. Now, that's not to say that an electron from 6 going to 2 couldn't also have gone 6 to 4 to 3 to 2. Sure, but every time it does that, it emits a photon. But that photon is representative of the energy between the levels, right? So what Bohr did was he said, okay, if I imagine this as the model, and I say the photon is dropped out, the photon is kicked out by the electron when it drops, then that means the photon's energy is the same as the energy difference. For example, if I'm looking at this one here, it'd be between these two levels right here. Right? The energy difference between these two levels is the energy of that photon. And that's how you find out what the wavelength of it is. So a couple of things come in here, and one of them is the energy of the photon is H times F, where H is the Planck constant and F is the frequency. So,
is there a way to predict what jumps the electron will make, or is it kind of like fully random?
there are ways to predict what jumps the electron might make, but there's no way to predict what jump the electron will make. Now, and that's the caveat to that is, I'm considering a particular situation. So let me take not the situation I'm thinking of. If I take this photon right here, or I construct a photon that has this energy difference, this energy, because it's the difference between the levels. If I have photons of that energy and I'm throwing them at hydrogen atoms, I expect that this will be the transition. I'm not expecting that to be the transition, because there's not enough energy in the photon to get it from here all the way up to here. It can go only here to here. So, in this case, in the case that I have a given energy in the photon, which means I've constructed my wavelength, right? Because really, I don't use this very often. Really, what you use is hc over lambda, right? Where the hc is the cool 1240 constant. Which, right? Did we run into that already? Yeah, we did. During the Compton. Or the photoelectric. One of those. I told you about this. So you just use hc over lambda, way easier. So I have a, laser, right, with a particular wavelength. And the wavelength, it gives me exactly the energy I need to expect an electron to make that transition. So in that case, I can predict that, yeah, it'll make that transition if it absorbs the photon. It's not going to make some other transition because the energy of the photon is only enough. It's like, right, I only have so much energy. I can go from here, or I can take the ball from the floor and put it on the table, and that's all I can do. Right? That's as much as I can possibly do. I can't take the ball and put it up to the ceiling because I don't have that much energy. So I can predict that that's what happens. The other part to that is I can't predict if the electron will quote unquote absorb the photon, right? So, or whether it'll ignore it, whether it wasn't quite the right one. So I can predict that it'll make the jump. I can't predict if it will, like, if that one's going to do it when I hit it with this one. I can't predict that. I can give you, like, maybe it will.
And there'd be no way to tell, like, if an electron in N4 would jump first to 3 and then to 2, or directly to 2.
Right.
Is that like 50-50, or is it kind of like there's some probability that that'll happen and we're not really sure?
You can calculate the probabilities that will happen, that will happen. Now, there are rules, right? There are rules about it can go 4 to 3 under certain circumstances, but it won't do it under other circumstances, and that has to go 4 to 2. Or even 4 to 1, and it can't go to 2 for some reason, whatever. But the idea being that that's what you do is calculate what is the likelihood that here's my electron up in the 5 state here. Is it going to drop to 2? Yeah, it could. Is it going to drop to 4? Yeah, it could. And I can tell you these probabilities, and we can calculate what these are. But as to what it's actually going to do, no idea. It's going to do one of those and they add up to 1. Right? Because it'll do something. I just don't know which one, ultimately. So Bohr was taking the energy of the photon. Yeah, there was some other thing. Oh, I remember what it was. Hold on, I want to hold that thought. I want to finish this first. So Bohr took the energy of the photon and he took the Balmer series, and I won't go through the whole rigmarole about how Balmer did his thing and how Bohr took that and figured out what was going on. Ultimately, what Bohr arrived at, which I will give you the Cliff Note edition here, is that the energy of a level, of an orbit in the hydrogen atom, right, is minus 13.6 EVs divided by n squared. So if I want to find what the energy of the ground state is, well, it's minus 13.6 EVs. And that correlates really well. By the way, I should put a little bit of perspective here. He did derive this number from fundamental constants. So that basically locked in the idea that this is a number for us to believe. Because it's literally a compendium of things like epsilon naught and pi and h and c, and you're going like, okay, they put together and you get this thing out. All right, that looks pretty good. Right? Gives you a little bit more confidence if you're able to do it from fundamental constants. Therefore, the changes in this energy here come about when the electron jumps, and therefore, if I want to figure out what the photon wavelength is, all I got to do is figure out what the energy change is. I don't know if I want to put an n right there, but you could do, and this is the one the chemistry people like to tell you all the time. It's the 1 over n squared minus the 1 over n squared. So you go, if it's a jump down, I need, what do I need? I'm going to get the sign wrong. I know I'm going to get the sign wrong. I always get the sign wrong. There's a difference here. So this is going to give you, if it jumps down, this is giving you a positive number. Yeah, that's okay. I got it. Oh, I did get it right. Your first time. If it jumps down, then, for example, it ends in the 2 state, and it started in the 5 state, so this is a positive number, meaning overall this is a negative number. And that makes sense because the electron went closer to the nucleus, so it should have lower energy there. Then that energy gets emitted by the photon in this form here, and it emits a particular wavelength, which we can then measure and confirm that, in fact, yes, this seems to be a useful model. So this is all great. This works perfectly well to describe the hydrogen atom. The problem is, once you go to helium, you got to fix it, because now it ain't going to work. And the reason it ain't going to work is because the mass of the nucleus is now 4 times what it was, because now in helium I've got 2 pluses and I've got 2 neutrons. So the helium nucleus is 4 times bigger, 4 times more massive, which then alters what the radius of the orbits are, which then changes the energies of the orbits, which does that, etc. Anyways, the good news is it basically turns out to be just a z squared. It just turns out to be a z squared. In other words, z being the, that's a good question. Z being the number of protons. Z being the number of protons. So for helium it would be 2. If I multiply energy by z squared, then I get the right energies. Right? So this is the modification for heavier atoms, heavier elements. But they can still only have 1 electron, because there's no electron-electron interactions here. You can't deal with those. You just don't want to deal with those. They're so horrendous. So the great news is, if you ionize helium, you take 1 electron, strip it away, this works great. So, but then you got to do all the stuff. Anyways. There are a number of corrections to it, because when I say it works great, it's not perfect,
It's good, but it's not perfect. And part of the non-perfection of it is in the analysis, Bohr assumed an infinitely heavy, right, nucleus. It doesn't move. Like, it literally is the sun compared to the planets. Now, yeah, is there a gravitational force on Earth from the sun? Yeah, therefore there's one from sun to Earth and Earth to sun, right? So does that mean the sun moves around a whole bunch because Earth is pulling it? No, it's like you jumping off Earth, right? You push Earth away. I tell the 4A people that, it's not really true, right?
You jump up, you go, oh yeah, I pushed Earth down. You didn't really. Not to any particular degree. So when Bohr did this, he assumed the nucleus was infinitely heavy and didn't move, but that's not really true. It wiggles around quite a bit. And so this is a great starting point, but you have to fix it up a whole bunch. Not a whole bunch. You can fix it up to make things better. Because people kept discovering things like they discovered that the photons weren't quite this wavelength, for example, right? Or if I put it in a magnetic field, it doesn't quite give me this wavelength out. Or maybe if I put it in magnetic field and then it splits these two, I could get this one or I could get that one. So there's all these extra little bits that come into the analysis. This is the basic analysis, but there's all the little bits that physics can put into it in terms of trying to find out what happens to an energy level when it's in a magnetic field, right? Well, I can't have an infinitely heavy nucleus anymore because it's going to be wiggling around. And I got to think about what the fine structure looks like. Okay, well, I got to do this, and I got to think about a Zeeman effect and blah, 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 right? So all sorts of fun things. The bare bones is this, and the reason this is good is because of the thing I want to tell you about right now, which for me is a great way of thinking about stuff like this. I think I'm going to use that picture right there, and I'm going to get rid of all this. Okay, so let's get rid of that. Okay, let's do it like this. I look at this and I think staircase, right? I called it like a ladder of energy levels, but I typically think of it as a staircase. It's just that the stairs get to be different sized, which makes it difficult to walk up and down. Something like that. I didn't quite get it right, but okay, you get the idea. And the reason I like this model is because I think I have memories. I think I went to my grandparents' house. They had this huge staircase, and I would be, those little toy cars. I'd just be rolling the toy cars down the staircase. Maybe that's the reason why I like it so much. But if you take a ball and you roll it down the stairs, right? That's exactly, okay, it's not exactly. It's kind of similar to an electron jumping down in an orbits here, right? So it starts here, and I have to just put on the caveat that every time it jumps a stair, I emit a photon, or it emits the photon. And if I give it a push, right, it could jump to this stair, or it could jump to this stair, or it could miss all of those and go down to here, or it could miss everything and go down to here, whatever, right? There are a number of different possibilities that could happen here. But like I said, we can calculate these possibilities. But at the bottom here, you grab the ball and you throw it back up. And then you watch it go boing, 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 and then you watch its path down again. And the path down is probably different than the first path. And it comes down here, you throw it back up there again. Okay, so this process is essentially like pumping the electron from the ground state up. You don't know how high you're putting it, right? So this is the physical equivalent, right? Taking the ball and just throwing it up there. Again, I could be throwing it all the way up here. I could miss and throw it and hit that step and have it bounce down here or something like that. So I don't know necessarily how far up I'm throwing it. But physically, the equivalent to that is essentially shining light of almost every wavelength on the thing, right? This is like blasting it with white light. Some light right? And white is gonna have some red in it. So some red light in there is gonna be able to only make it go from, say, here to here. But if I put blue light in, it's gonna make it all the way up to here. Or if I get an X-ray in there, boy, it's all the way over there. Or actually an X-ray would ionize it, so never mind. But the point being that that's like what we typically do when we try to excite a gas such that we can then observe the consequences of the electron dropping, which is to say, oh, I see these particular colors coming out, right? Now, back to your question, which was, well, how, does it have to go 6 to 2 or could it go 6 to 5? Yeah, it can, but we can't observe that. Not that we can't observe it, we can't see it. Because think about how much energy this is, right? Compared to something like this. If I tell you this is the light, this is violet light for hydrogen, right? Then this is like in the infrared. You have basically nothing, right? This is red, that's the edge of our seeing. That's the other edge of our seeing. That's way under our seeing. So we can't see it, but it's there. And as soon as they developed the technology, then everybody got a series name. Everybody figured this out. So Balmer gets the series that's the visible one. Lyman gets the one in which the ending state's the one, because everything there is in the ultraviolet. And they didn't have ultraviolet detection in the 1910s or 20s or whatever. And then somebody else got the 3-1 because that's in the infrared, and somebody else gets their name on the 4-1. So any electron that drops down and ends in the 4 state has a name. It's whatever it is. I don't know what it is. Really like the staircase model because I find it to be applicable outside of this. So for me, the big reason that we're talking about the Bohr model is in order to develop the idea of the thinking of the staircase model. That to me is the big thing. Okay, so let's do this. All right, what I want to do then is let me show you some of this in action. I'll show you some of the math in action, and then we'll talk about why. Yeah, we can do that. We can talk about why these orbits are the ones that get occupied. Maybe we can. All right, skipping all that and going to what? Here, yeah. Okay, I calculate, so I want to do, okay, let's do this. I calculate the Balmer series, wavelengths. The Balmer series wavelengths, so this would be, for example, which I kind of just erased a little bit of, but this would be, for example, the 3 to 2, 4 to 2, 5 to 2, and 6 to 2. All right, so if we take the 3 to 2, the 3 to 2 transition would have a delta E of minus 13.6 EVs times 1 over 2 squared minus 1 over 3 squared. Okay, so this gives you a particular number, which you then put into that delta E equaling HC over lambda. Well, really it's negative of that. Okay. Now, the reason we do this is because of the energy. So the idea that so just a quick aside, why these are off by a negative sign, the delta E plus the HC over lambda should equal 0. By energy conservation, the change in the electron's energy, which is this, plus the photon energy, which is that, should be conserved, right? In other words, energy's not coming anywhere. It's not coming out of anywhere or going anywhere. Change in electron energy. that is the reason that the electron energy change as it drops towards the nucleus should be negative, and the photon energy should be positive, so it's going to come out as a positive wavelength, which is what you need. Therefore, if I wanted to say, okay, I want to find lambda, let's find the wavelengths. Okay, so I'm going to take HC and divide it over here, and then I'm going to flip them over. So I'm going to get HC divided by the negative of the change in the energy. So just to give this a little bit of numeration here, we're going to find it's HC divided by all of this stuff. When you do that calculation, it turns out to be, no it doesn't, what does it turn out to be? 1.9? It's 3.4 and 1.5, so it's about 1.9 EVs. Oops, I forgot the HC. I should put the 1240 in for the HC here. That seems reasonable. Is that what you got?
Yeah.
Because this is a number like 3.4 and that's a number like 1.5. So about 1.9 should be about right. And that's a nice rule of thumb. If it's a visible photon, the energy in EVs is like 1 or 2, or 3, around there, right? Just a couple of EVs for the visible photons. As soon as you start getting into, oh, I got a 15K EV photon here, you're going like, whoa, point that somewhere else, right? That's like in the X-ray.
This is the red line you'd see in the hydrogen emission spectrum.
So this is the red line that you'd see, and you get a 6, if I remember, it's like a 656 point something or other, nanometers. And so that would be the red, that would be the calculation of the red emission here between the 3 and 2 states. And then you can go to the 4 and 2 states and find it's kind of a green, and then you go to the 5 and find it's kind of blue, and then you go to the 6 and find it's a violet. And so barely in the seeing range. Typically, it's, for me, it's really hard to see the violet one. But those 4 lines are the like benchmark, spectrum from the hydrogen, right? So great. Balmer did all of that work whenever it was 18 something or others. And Bohr has given it some physics and has showed that we can actually calculate these things. All right. Now, I told you at the beginning this is not how we think about things, but again, it's really useful, okay? And I should be careful. Photon energies, yeah, that's what they are. It's not that we don't think about them that way, because that's what they are, but we don't think about the way he did this, which was kind of classical in the sense that he took the centripetal force on the electron and he looked at the angular momentum and he did this and he was like, well, so we don't really do it that way anymore. But the idea that he came out with, which for me is this idea of like ball rolling down a staircase and emitting photons type of thing, is really useful. So let's maybe go into a little bit more on the more modern formulation of what we see when we look at the hydrogen atom. Because I remember that last time we talked, which was so many weeks ago, apparently, I think I finished that one talking to you about the de Broglie hypothesis, which was the idea that there's a wavelength associated with things with momentum. We were just talking about this when we left last time, when I saw you last. And that's the relationship for the photons, right? This is the relation for the photon. And de Broglie is saying, hey, why not everything? Why not anything that's got momentum to it? So, as unbelievable as it sounds, this is actually useful. So let's talk about this. In other words, electrons with a particular momentum are going to be wave-like in their natures, I guess is what you'd say. And I want to just I want to take a minute or two here to just describe the double slit experiment from the electron standpoint. Okay, double slit experiment is the same one we did in 4C, where I have a laser back here. I'm shining it onto a two-slit arrangement like so, and I'm noting the interference pattern that falls on the screen here. And so I notice, and we talked a little bit about this, I remember. So I noticed that if I cover this slit up, then I get a single slit pattern, which is more or less centered around light coming through the upper slit here, right? So you get the big central maximum here. And then if I cover the upper slit and I let the lower slit be here, I get the central maximum kind of over here where the lower slit is. But then when I let them both get after it, I lose like the identity of one slit versus the other, right? And now we're dealing with both of them together. So you get this interference pattern, which has a maximum in the middle, and then I'm just going to draw the interference pattern, not the diffraction along with it. You get this thing, oops, that's a little high, like that, like this, right? You get this thing here. All right, so with light, no problems. And maybe you used, I don't know, you could even go through with this thing and you could say, maybe I used maybe I used a red laser, right? Maybe the red laser has a wavelength close to 650 or 620 or whatever it is. But you can then figure out how much momentum to give an electron in order for it to have the exact same wavelength. At which point you find the exact same pattern happening. So we find that this is true not only for light, but also is useful for, true for, we find all quantum mechanical particles, of which the electron is one, the photon is one, but also the proton, the neutron. These are heavier things. I will admit to my knowledge being a little bit dated on this because I haven't checked recently, but last I looked, they were still, and it wasn't quite exactly the same thing, but you could still get wave behavior from a molecule containing 60 carbon atoms. A buckyball is what those are known as. And so a buckyball still shows a little bit of, right, big kind of a central maximum, but it still shows a couple of these tails when you shine it through a slit. So the question is, where's the dividing line here? What are we calling macroscopic? What are we calling a quantum particle? The problem is there isn't really a great dividing line, because I don't know about you, but I hear a C60 and that's like a dump truck. You're dealing with something that's like incredible, right? The size and the mass of this thing. I'm going to drive a dump truck through a toll plaza and expect my dump truck to suddenly be over there. And you're going like, what? Makes no sense. But here we are. That's the thing we deal with. So a more modern formulation of why do the electrons occupy these particular orbits in the hydrogen atom. I should probably move a little bit over here so I'm not totally off the screen, like here. So here's our hydrogen atom, and here's our orbits, which I told you aren't true. And they're not. But if we take this to be, say, I don't want this to be like the 1 orbital, maybe this is, say, the 3 orbital or something like that, okay? Why does it occupy that orbit? And not an orbit between here and here? Right? How come it occupies that one or that one, but not anything in between? And it's because we kind of give it a little bit of this idea here. So I have to think how I'm going to draw this. I got to plan this one out a little bit. Okay, all right, we're going to go for it. I don't know how this is going to work out. I'll do it in red. We're going to go like this. We're going to go. That's not quite what I wanted it to look like, but then nonetheless, if the wavelength of the electron is such that it goes around this circle in a standing wave pattern and connects, then this is an allowed orbit, right? This is the wavelength of the electron that's in that orbit with 3 lobes to it. And if it's in the 4 state, then you'd say it looks kind of like this. Well, I'm going to draw right on top of it, which is unfortunate, but it's going to look something like that. Not great. I had to, that's what I have to deal with. Like that. Okay, something more like that. Where the wave of the electron is a integer number of kind of like the circumference of the orbit, say, right? Pretty cool. So the more modern formulation of the electron orbits are ones in which the electron creates a standing wave pattern in that orbit, and between them, and this is exactly what you would have seen in the 4A stretched string lab, right? You go from a frequency of 5 hertz to a frequency of 6, and all of a sudden the pattern disappears, right? And that's what happens. If it's destructively interfering in between these two things, you don't see the electron having an orbital allowed in here because it can't exist there. So it constructively interferes here and here, but destructively interferes everywhere else.
For standing waves on like a string.
Yeah.
I was like, it's like going in one dimension and then hitting your infinite boundary and coming back superposing.
Yeah.
How does that work for like 3-dimensional things? Because like we've drawn this to be like 2D.
Yeah.
But I would assume that the electrons kind of like spread probabilistically in 3 dimensions. Yep. Does that mean that it has to be like standing wave along each axis? And if so, is there like that symmetry?
Yeah, there's still the symmetry, and the good news about these ones is that they're spherically symmetric. So you can think of, instead of just thinking of a string, you can think of like a sheet, like a drum head or something like that, right? And you can think of the if you wrap the drum head around, then you're thinking about the lobes that the drum head makes as it tries to form a standing wave pattern when you shape it into a ball. So in the 3D sense, things are not really more difficult because the math takes care of it, but they're more difficult to visualize, right? Like even when you go from a string to a drum head, even if you stretch the drum head and you're just looking at vibrations of the drum head on a 2D plane, you're going like, I don't know if I can see how that looks. Like that's got something here and then it's dipping there and coming like this, but at the same time it's doing this way.
Is that like Bessel functions?
Yeah, that's one of the things that we got to use. Yeah, the spherical Bessel functions. And then going into 3D, yeah, I mean, hey, I say good luck. I mean, the problem is we live in a 3D world, we can't even visualize it, right? It's hard. It's hard. So we actually have a demo of this, and maybe I can show it to you at some point, which is we just have metal circles, and if you put them into that string vibrator, you see the patterns. That's what they look like. And so it's just the electrons doing the same thing. I mean, but as you said, like in 3D instead of 1. Can't be perfect.
That would be cool to see.
All right, so a couple of things. I don't want to go too far into the Bohr model because I've talked to you about that. So why don't we do this, which is, I think, going to be useful. All right. Yeah, no, we're probably going to call that for today. Okay. Since I've been talking about the more modern formulation is the Schrodinger equation. So let's talk about the Schrodinger equation. Now, this is a pretty nifty formulation, but it's not the only one. It's just the one that's gained the most traction because it's useful for calculating. The calculations are pretty straightforward. Obviously, it does what it needs to do in terms of predicting measurable quantities. And it has the wave function, which ultimately is nice as a visualizing tool. But it's not the only formulation of quantum mechanics in the non-relativistic sense. The Heisenberg representation, also very fun to use, and was one that I actually liked a little better than the Schrodinger formulation, but nonetheless, this is the common one, so we're going to use that. But just letting you know, just because we're focusing on talking about this one doesn't mean it's the only one. Just like we talked about, actually we didn't talk about GR. Sometimes I do a little bit on GR, but maybe we'll have time for that later. But that's one formulation, right? It's not the only one. Just turns out it's the one that's the most correct. But there are other formulations of GR made by other people. Anyways, this is the most useful one that I think there is, but not the only one. And I'm not going to go through a full motivation of why the equation looks like this, but I will motivate parts of it. It looks fairly interesting. In one dimension, we will do the one-dimensional time-independent. We'll do psi of x. I'll call this v then. Psi of x. And we'll say that we're going to do time-independent, so we're going to do an e times psi of x. All right. This is the Schrodinger equation, and it is in one dimension, and it's time independent. In other words, why are we calculating the time independent one? Well, because what we're looking for here are stationary states. And stationary states are useful because, just like I was telling you with the electrons in the orbits, right? You want to come to basically a standing wave solution. That's what a stationary state is. Like you remember the string, and it looked like the wave wasn't moving, but it is, right? They're moving back and forth and they're constructively interfering in this, that, and the other. So we're doing the time-independent one because what we want to establish is a pattern for the wave function, and we want it to be not changing in time, at least to start off with. If we have time later at the end of the class, we can talk about what it looks like when it really starts waving. But this is the one we're dealing with right now, and it's the, like I said, the one-dimensional, so you're only seeing x's in here, and not depending on time. What is this thing at its heart? It's energy conservation. This is nothing more than kinetic energy, potential energy, and total energy. That's all this is. I should really do that, link to there. All right, so really it's just a kinetic energy term, and why this gives you the kinetic energy, well, that's something we don't really have time for, but you can motivate it if you do look at how a wave function looks for a free particle and then said, okay, here's what kinetic energy is, momentum squared over 2m, right? P squared over 2m for a free particle. So typically what's going to happen here, and you'll notice also this is an eigenvalue equation. So our total energies are our eigenvalues, and the functions that satisfy this, when we put in, we typically are the people who then decide what the potential energy function looks like. And then you bash this thing out in order to solve for what the wave function looks like. And those wave functions are your eigenfunctions. Now, what good is the wave function? So the wave function by itself is a useful visualization tool, but I put length instead of function. But its real power comes in when you square it and look at what that means. Wave function, psi of x and squared dx. If I square the wave function and then I multiply by a differentially small piece, mathematically dx, but in reality it would be a delta. And I look at the multiplication of these two, this is ultimately interpreted to be the probability of finding, I'm going to assume it's an electron that's being described by the wave function. Probability of finding that electron in the area, I should not say area, in the length, I'm just saying dx. It's the probability of finding the electron in dx, such that if this was a delta x, right, then this would be a delta x. And that's why I said the measurement part, right? If you want an actual finite space, psi squared times a delta x is the probability of finding the electron in that delta x. And since you insist on having an electron, you should be able to find it somewhere, and this is the thing we were talking about, right? You should find it somewhere, which means that the wave function should be normalized. If I take all of these probabilities and add them up through all of space, I should find the probability to be 100% that I found the electron somewhere in there. All right. So what I will leave you with today, since I think I'm just about out of time here, is that next time what we're going to do is pick the easiest possible potential energy function, and it's known as the infinite square well. And it looks like this, where these things go up to plus infinity. The sides of the well go up to plus infinity, and the bottom of the well is at 0. So this is your standing wave on a string, right? It hits this thing, which causes it to be completely confined, and it goes back this way, causes it to be completely confined. So you know the electron has to be in here somewhere because it can't exist out here where there's a potential energy of infinity. We'll pick up with this one. This is a this is a pretty nice example, because everything that happens here is exactly describable by the stretched string. And Griffiths will tell you the same thing, right? That you can actually go through this, calculate what the wave function is going to be, look at what the normalization constant is going to be, and then have it work out exactly the way you'd want it. And this is also really useful as a mental tool for thinking about what does the wave function look like when you get to different potentials, right? So what if I had something that had a step in the middle, or what if I had a barrier in the middle, or what if I had a well here, or what if it was looked like this, or what are the, so we want to start looking at what does the wave function look like in particular situations, and then using that to try and see if we can enhance our physical intuition about it, because really this is the only thing you have. Solving quantum mechanics problems is basically about doing something with the Schrodinger equation, mathematically. In terms of a visualization tool, I mean, the more you have on the wave function, the better, because that's pretty much it. There's nothing else. I don't know. I can't really visualize this thing the way it stands like that. Okay. So, cool. So we'll pick up there on Friday next week. How about that? Sound good? And if you're watching this, sounds good, because you got a say in this. All right, see you later.